Today we are going to learn about mastering linear combinations in vector spaces. We'll explore how to construct and analyze linear combinations, a crucial skill for applications in data science and machine learning. Welcome to our video on mastering linear combinations in vector spaces. In this introduction, we will define what a linear combination is and explain its significance in the study of vector spaces. A linear combination involves adding two or more vectors together, each multiplied by a scalar coefficient. This concept is foundational in vector spaces and crucial for understanding more complex mathematical and computational tasks. Throughout this video, we will explore examples, geometric interpretations, applications in solving equations, and its role in data transformation and reduction. Our goal is to equip you with the skills needed to construct and analyze linear combinations, paving the way for applications in fields like data science and machine learning. Let's delve into the definition of linear combinations. A linear combination of vectors involves the summation of multiple vectors, each scaled by a corresponding scalar. Mathematically, if we have vectors v1, v2, vn and scalars a1, a2, and then a linear combination is expressed as a1 v1 plus a2 v2 plus and vn. The scalars can be any real numbers, and the vectors are elements of a vector space. A crucial aspect of linear combinations is that they allow us to express one vector in terms of others, facilitating transformations and manipulations within the vector space. For example, in a two-dimensional space, the vectors 1, 0, and 0, 1 can be combined with appropriate scalars to form any other vector in that space. Understanding the basic properties of linear combinations, such as closure and distribution, is essential for further exploration of vector spaces and their applications. In this section, we'll explore linear combinations in two-dimensional spaces. Imagine a simple 2D coordinate system with the unit vectors I equals 1, 0 and j equals 0, 1. These unit vectors can be linearly combined to create any vector in the plane. For instance, by taking two scalars, a and b, we can form the vector ai plus bj equals a, b. This linear combination allows us to represent any point on the plane as a vector. Consider practical examples. Combining vectors 2, 3, and 4, 1 with scalars 0.5 and -1, respectively, results in the vector 0.5, 2, 3 plus -1, 4, 1 equals 1, 1.5 plus -4, -1 equals -3, 0.5. Such combinations illustrate how we can manipulate and construct new vectors using existing ones. This foundational skill is invaluable for understanding geometric transformations, solving equations, and modeling real-world phenomena in two-dimensional space. The geometric interpretation of linear combinations is crucial for grasping their significance in vector spaces. When we add two or more vectors, we essentially perform vector addition, which can be visualized as placing vectors end-to-end, forming a resultant vector. The direction and magnitude of this resultant vector depend on the original vectors and their respective scalars. For instance, in a geometric space, combining two vectors can represent a translation or shift from one point to another. Scaling these vectors changes their magnitude but not their direction, assuming positive scalars. Negative scalars, however, reverse the direction. This visual representation helps us understand transformations within vector spaces intuitively. By examining how vectors can be scaled and combined, we gain insights into their roles in geometry, physics, and computer graphics, where transformations like rotations, translations, and scaling are commonplace. Linear combinations play a vital role in solving systems of equations, a common problem in algebra and linear algebra. When faced with multiple simultaneous equations, we often seek to express one variable in terms of others, a task that can be efficiently managed using linear combinations. Consider the system of equations, 2x plus 3 years equals 5 and 4x, y equals 6. By manipulating these equations through linear combinations, such as adding or subtracting multiples of one equation from another, we can isolate variables and find solutions efficiently. Moreover, linear combinations can be represented using matrices, where each row corresponds to an equation and each column to a variable. This matrix representation simplifies complex problems and connects to the concept of linear independence, which determines if a unique solution exists. By mastering linear combinations, you gain a powerful tool for solving practical problems across various fields, from engineering to economics. Linear combinations are essential in data transformation and reduction, particularly in the context of big data and machine learning. Techniques like principal component analysis, PCA, leverage linear combinations to reduce the dimensionality of data while preserving its essential features. By representing datasets as vectors and forming linear combinations, PCA identifies principal components that capture the most variance in the data. This process transforms high-dimensional data into a lower-dimensional space, making analysis more manageable and computationally efficient. Moreover, linear combinations facilitate feature extraction and selection, crucial for improving model performance in machine learning. By understanding the role of linear combinations in data transformation, you can enhance data preprocessing, optimize algorithms, and achieve better insights into complex datasets, ultimately leading to more effective decision-making and predictive modeling. While working with linear combinations, it's crucial to avoid common mistakes and pitfalls that can lead to inaccuracies in calculations and interpretations. One frequent error is misinterpreting vector directions, particularly when dealing with negative scalars that reverse a vector's direction. Another common mistake is applying incorrect scalars, which can distort the intended transformation or combination. Neglecting the concept of linear dependence can also cause problems, as it might lead to redundant vectors that don't contribute new information. Additionally, overlooking the geometric implications of linear combinations can hinder understanding of transformations and spatial relationships. Finally, errors in matrix operations, such as incorrect row manipulations or element-wise calculations, can result in flawed solutions. By being aware of these pitfalls and meticulously verifying your calculations, you can ensure accurate and reliable results while working with linear combinations. Let's put theory into practice with a hands-on example of linear combinations using Python. Python provides powerful libraries like NumPy and SciPy that facilitate mathematical computations. We'll start by importing NumPy and defining two vectors, v1 equals np.array2, 3, and v2 equals np.array4, 1. To create a linear combination, we'll use scalars a equals 0.5 and b equals -1, then compute the combination using the formula combination equals of v1 plus bv2. This results in the vector combination equals np.array-3, 0.5. Interpreting these results involves understanding the transformation applied to the original vectors, resulting in a new vector in the same space. This example demonstrates how linear combinations can be implemented programmatically, providing insights into their applications in real-world data manipulation and analysis. By mastering these coding techniques, you can efficiently handle complex datasets and perform advanced data transformations with ease. Linear combinations are integral to numerous real-world applications in machine learning. In feature engineering, linear combinations assist in creating new features from existing ones, optimizing data representation for model training. This process enhances data preprocessing by transforming raw data into a more suitable format for analysis. Techniques like dimensionality reduction, including PCA, rely on linear combinations to reduce data complexity while preserving essential information. This reduction not only improves computational efficiency but also enhances model accuracy by eliminating noise and redundant features. In supervised learning, linear combinations help construct predictive models by combining input features to form decision boundaries or regression lines. By understanding and applying linear combinations, you can unlock the full potential of machine learning algorithms, achieving more accurate predictions and insightful analyses across various domains, from finance to healthcare. As we delve into advanced concepts, let's explore the ideas of span and basis in vector spaces. The span of a set of vectors is the collection of all possible linear combinations of those vectors, representing a subspace within the larger vector space. Understanding span is crucial for grasping the structure and capabilities of vector spaces, as it defines the reach of the vectors used. Basis vectors, on the other hand, form a minimal set of vectors that can span the entire space. These vectors are linearly independent, meaning no vector in the basis can be expressed as a linear combination of others. The connection between span and linear combinations is pivotal in vector analysis, as it allows us to define and manipulate subspaces effectively. Applications of span and basis range from solving systems of equations to analyzing dimensions in higher dimensional spaces. Mastery of these concepts is essential for advanced studies in mathematics, physics, and computer science, where vector spaces play a significant role. In this block, we'll extend our understanding of linear combinations to higher dimensional spaces. While two-dimensional and three-dimensional spaces are relatively easy to visualize, higher dimensional spaces present unique challenges. A key aspect is extending the concept of linear combinations to n-dimensional vectors, where the principles remain the same. Vectors are combined using scalar multipliers to form new vectors within the space. Visualizing these spaces can be difficult, but tools like projections and coordinate transformations help represent higher dimensional data effectively. Linear combinations in higher dimensions are crucial for analyzing complex datasets, particularly in fields like machine learning and data science, where data often exists in multiple dimensions. Moreover, they play a significant role in theoretical studies, such as quantum mechanics and advanced algebra, where understanding the behavior of vectors in multidimensional spaces is essential for problem solving and innovation. As we conclude our exploration of linear combinations in vector spaces, let's recap the key concepts covered. We've defined linear combinations and explored their applications in various fields, from data science to machine learning. We've seen how linear combinations enable us to solve systems of equations, transform data, and analyze complex datasets. Understanding linear combinations is fundamental for mathematical and computational tasks, providing insights into the structure and behavior of vector spaces. We encourage you to delve deeper into this topic, exploring advanced concepts and real-world applications. Numerous resources are available for continued learning, offering opportunities to enhance your skills and knowledge in this fascinating area of study.